Welcome back. In this video, we will continue to learn about organic chemistry. We will somewhat summarize the different things that we've seen and apply them into a biological context. So we've talked about alkanes, alkenes, and alkynes. If you take an alkene or an alkyne, we've described how they have double bonds or triple bonds, and they're what we call unsaturated hydrocarbons. We can also have what are called cycloalkanes. We've seen some examples of those, where you have ring structures. Cycloalkanes are also examples of what are called unsaturated hydrocarbons. And this term unsaturated simply means that they have fewer hydrogens than they could potentially have based on the number of carbon atoms that are in the molecule. And so each ring or each double bond or triple bond, each double bond adds 1 degree of unsaturation. So if you have a molecule with a triple bond, then this adds 2 degrees of unsaturation. And that means that for each one of those degrees of unsaturation, we have 2 fewer hydrogen atoms in the molecular formula. So an example of a saturated fatty acid is stearic acid. In this particular molecule, you can see that the carbon-carbon bonds are all single bonds. Whereas for oleic acid, we do have a double bond. That changes the structure of this molecule and provides it with different properties. So this would be an example of an unsaturated fatty acid. And these, again, the level of saturation affects the properties of those molecules. If we look at a cartoonized version of these molecules, you can see that stearic acid has a probability of being straight-chained in a somewhat linear manner, whereas oleic acid, due to that double bond, it has a kink in the center, which tends to bend it off in a different direction. And what this ends up doing is it changes how these molecules interact. And we'll learn later about what are called intermolecular forces. But essentially, we see that stearic acid is able to stack better. And because of that, it ends up with a higher melting point. Whereas oleic acid is not able to stack as well. They don't interact as much. And so it has a lower melting point. And we see this in practice. If you go to your pantry and you look for a stick of butter, butter is a fat. It consists of fatty acids linked together, and many of those are saturated fatty acids. So they fall into this category here. Whereas if you have a bottle of oil, those oils have high amounts of unsaturated fatty acids, and therefore they tend to be liquids at room temperature. We can also see aromatic biomolecules. So we discussed how aromatic compounds are those that have ring structures with alternating double bonds and single bonds. Adenine is one of the 4 bases that's found in RNA and DNA. And you can see that it has these 2 fused rings, 2 ring structures that are stuck together. And we have an aromatic ring in the larger 6-membered ring. And these aromatic biomolecules, the fact that it's aromatic, changes its properties relative to what it would be like if it were not. And so we end up getting very flat bases here. And this is what allows DNA and RNA to stack well, is the fact that it's aromatic. That means that it ends up being flat, and therefore they can stack together and form our DNA double helices. All right, one last thing that we want to do is practice again thinking about the relationship between structures. We've talked about different types of isomers, constitutional isomers, geometric isomers, You also could have molecules that are the same molecule, but they just look perhaps different. They've just been rotated in space. And so it's important to be able to recognize those. We could also simply end up with two structures that are just not even isomers. They're completely different molecules. And so this is a flow chart that I recommend that you use that can help you to identify any two molecules to see, are they the same? Are they constitutional isomers, geometric isomers, or are they completely different molecules? So let's practice this on this set here. So the first thing that we want to do is identify the number of carbon atoms, the number of other atoms. These are called heteroatoms. This includes things that are sulfur, nitrogen, oxygen, phosphorus, fluorine, chlorine, etc. So essentially anything that's not carbon or hydrogen. So we want to count up the number of carbons, the number of each heteroatom, and then evaluate to see if they have the same degree of unsaturation. Okay, so let's do that. Here on the left, this is an amino acid called tryptophan. We can see we have one nitrogen, two nitrogens, two oxygens, and then we have a carbon, a carbon, a carbon, 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 and then 6 more carbons in this ring. Okay, now considering the degrees of unsaturation, what we're looking for here are rings, double and triple bonds. So each ring counts as 1 degree of unsaturation. We have 2 rings. Okay, each double bond counts as a degree of unsaturation. And it's a little bit hard to tell. Let me erase some of these carbons. We have 1, 2, 3, 4, 5 double bonds. So that is 2 rings, 5 double bonds. That means that we have 7 degrees of unsaturation. So for molecule 1, we counted up 2 nitrogens, 2 oxygens, 11 carbons, and 7 degrees of unsaturation. Now I want you to try on molecule number 2. Pause the video, see if you can figure out how many nitrogens, oxygens, carbons, and degrees of unsaturation we have. Welcome back. Let's see if you got it right. There are the same number, 2 nitrogen, 2 oxygen, 11 carbon, and 7 degrees of unsaturation. The nitrogens here, oxygens are here. Those are fairly easy to pick out. Carbons, we've got carbon here, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, and then degrees of unsaturation. We have 2 rings. We have 1, 2, 3 double bonds, and we have 1 triple bond. Triple bond counts as 2 degrees of unsaturation. So that means we have 5, 6, 7 degrees of unsaturation. So these have the same molecular formula. Now, you could have counted up the number of hydrogen atoms, but by identifying the number of carbons, heteroatoms, and degrees of unsaturation, you actually don't even have to count up the hydrogen atoms. That will work every time. The next question is, do they have the same atom connection? It's a little bit harder to tell with all of the writing we've done on it, so let's erase that. But hopefully you can see once we do that fairly easily that these definitely do not have the same connectivity. These are very different looking structures. So the answer there is no. So these are what are called constitutional or structural isomers. Alrighty, I think that is it for this video. Thanks very much for watching and have a wonderful day.